Hello everyone, my name is Mohammad Reza Paidari and I'm a PhD student at Simon Fraser University. Today I would like to talk about my machine learning course assignment. In this assignment, I developed several machine learning regression models to predict hourly bike rental demand using the bike sharing dataset. And my goal was not only to build prediction models but also to understand the complete machine learning workflow starting from data exploration and pre-processing, then model development, performance evaluation, and finally comparing different regression algorithms. I implemented 5 regression models, including linear regression, ridge regression, polynomial regression, support vector regression, and random forest regression. Then I compared their performance using root mean square error and R squared to determine which model performed the best. First, I load the dataset and inspect its structure. Before doing any machine learning, I always want to understand the data. So I check the dataset size, preview the first few rows, verify the data types, and check for missing values and duplicate records. And one important pre-processing step is removing the casual and register columns. I remove these because their sum is exactly equal to our target variable, which is count. If I kept them, the model would effectively know the answer during training, which is called data leakage. This is probably the most important part. I'm going to talk about my exploratory data analysis. Before training any machine learning, we should do this because it helps me understand the behavior of the data. The first 3 figures help me understand the basic behavior of the dataset. I observe that bike rental demand is positively skewed. Demand increases over time, and working days show 2 clear commuting peaks around 8 a.m. and 5 p.m. This observation indicate that time-related variables such as hour, months, and working day are likely to be important predictors. The next figures investigate seasonal and weather effects. Demand is generally higher during warmer season and decreases as weather conditions become worse. This result confirmed that environmental variables should also be included in regression models. The remaining data analysis focus on the relationships between the numerical variables and bike demand. Temperature shows a positive nonlinear relationships, humidity shows a negative relationship, and wind speed has a smaller effect. The correlation analysis also confirms that time and temperature related variables are among the strongest predictors. From this analysis, I already expected nonlinear machine learning model to outperform simple linear regression. Now, let's go to train and test our dataset. After understanding the data, I prepare the training and testing dataset. Instead of randomly splitting the observation, I use a chronological 80-20 split. I choose this because the data has a time sequence. Using future observations to predict the past would create information leakage. This chronological split better represents a real forecasting problem. Next, I prepared a pre-processing pipeline. I standardized the numerical variables for linear regression, ridge regression, polynomial regression, and SVR because these algorithms are sensitive to feature scaling. Random forest does not require scaling because it is based on decision trees rather than distances. Finally, I created reusable evaluation functions so every model is evaluated consistently. Next, I trained 5 regression models. Linear regression provides a baseline regression, investigate whether regularization improves the linear model. Polynomial regression captures nonlinear relationships through feature expansion. Support vector regression uses a kernel function to model more complex nonlinear behavior. And finally, random forest combines many decision trees to improve prediction accuracy and reduce variance. Based on the nonlinear patterns I observed during the data analysis, I expected random forest to perform the best. The final comparisons confirms my expectation. Linear regression and ridge regression achieve similar performance because both are fundamentally linear models. Polynomial regression improved the prediction accuracy by capturing nonlinear relationships. Support vector regression performed even better, while random forest achieved the lowest testing root mean square error and the highest testing R squared. The feature importance plot also agrees with my data analysis by identifying hour, temperature, and seasonal variables as the most influential predictors. In conclusion, this assignment helped me understand the complete machine learning workflow from data exploration and pre-processing to model development and evaluation. The most important lesson I learned is that understanding the data before building the model is really essential. Since the dataset contains several nonlinear relationships, the nonlinear model consistently outperformed the linear model, with random forest achieving the best overall performance among the other ML models. Thank you so much for listening to me about this assignment.